Okay, good evening, everybody.
Good evening.
And welcome to another session of organic chemistry. In today's session, we are going to finish our discussion on chapter 22, which is concerned with the chemistry of Enolate and ions. Before we get the session started, I do have a few announcements to make. A reminder that on Tuesday, April 9, we are going to have the third class exam. And because of that exam, tomorrow, Friday, April 5, we are going to have an online review session. That is at 8 p.m. So I will send you a reminder tomorrow. Also, I also want to remind you when you come in on Tuesday for the exam, there will be seat assignment. Your seat will be assigned. And also, when you write on your exam, please do not write in the back of your exam papers, because we are not going to grade any questions in the back of the papers. If you need extra sheet of paper, we'll give you the extra sheet of paper. At no time should you write on the back of the exam papers. Of course, then finally we have your homework for this week. It's due on Sunday. That is April 7th at 11 p.m. So what we want to do now, let us discuss the problems from the quiz that you guys have just taken. Okay, Jaconda, can you go ahead and read this for us?
The following reaction does not involve an Enolate anion. However, it is a variation of nucleophilic acyl substitution reaction. Provide a mechanism.
Okay, thank you. Okay, so what they are testing here is your knowledge of reaction mechanism, particularly in regard to the chemistry of carbonyl compounds. So what do we have here? We have an alpha bromocyclic ketone, this molecule here. And then we also have hydroxide in the form of sodium hydroxide. And this molecule has rearranged from a 6-member ring to a 5-member ring. Okay, so therefore we have to give the mechanism on how this rearrangement has occurred. Okay, so let's do this together. What do you think is the first thing that happens? Of course, they told you no Enolate ion. No Enolate ion. So what will be the first thing that will happen? The hydroxide will attack the carbonyl. Okay, very good. Good. So the hydroxide comes. Attack this, the hydroxide acting as a nucleophile, attack that carbonyl carbon because it is electrophilic, and of course this pi electron goes to oxygen. So we have this intermediate. Okay, we have the methyl here, another methyl here. Okay, so now, what happens after that? What happens after that? We have an alkoxide intermediate. So what do you think will happen? Keep in mind we are going from a 6-member ring to a 5-member ring, yes. Will reform. Okay, very good. The double bond will reform. I believe it was one of you guys that said that some time ago. The double bond will reform. Okay, and then, okay, I tell you what, let me help you out here. Let me number the carbons. Let us number the carbons. Say this is carbon 1, 2, 3, 4, 5, and 6. Okay. Okay, so the double bond is going to reform, you said? Okay. And then when the reform, also let me number this carbon here. This is 1, this is 2, 3, 4, 5, and 6. Okay, so when it reforms, something has got to break. There has got to be some kind of bond cleavage, right? Because we know carbon cannot have more than 4 bonds. So what bond is going to cleave? Just give me the numbers. 1 and 2, okay? You say 1 and 2 is going to break. So you're going to break this here. And then when that happens, what is going to happen? Attack the, okay? So this bond will break, 1 and 2 will break. And then almost as though you are having an intramolecular SN2 reaction. Okay? And this will be, the bromine will live as a living group. And then what do we have? So you guys already know mechanism then. So we have this. Okay, I will say this is carbon number, this is here, and this here is here. Let us number the carbons. So this will be carbon 1 right here. Okay, and this will be carbon 6 right here. 5. And this is 4. This is 3, and this is carbon number 2. Is that correct? Okay. Okay, so once you, then what happens after that? You get your product, right? Yeah. Then what? then why do we need this here? Why do we need the hydronium ion? You got to ask the question, why do we need the hydronium ion? What? Lana? Say that again. To stabilize it. No, okay, now, look at what you have here. You have a carboxylic acid. You have hydroxide. What do you think will happen between carboxylic acid and hydroxide? There will be an acid-base reaction. Okay, so therefore, what happens, because you have that base, so here, this comes here, picks up the, so you end up with the carboxylate. Okay, and then finally to get this, of course there's water here, and finally to get this, you then add dilute acid. Okay, so the The dilute acid is simply just to protonate the carboxylate that is formed. Okay.
So if you stop here, then it's
If you stop here, this is what you get. Because when right.
for the addition
Huh?
do we have to do this step, the addition of the hydroxide?
No, if you don't do it, I'll let you go. That's fine. That's fine. Okay. But anytime you have carboxylic acid and it is in a basic solution, it will exist in form of the carboxylate, not in form of the free acid. Okay. Okay. So, but if you just get to here, that's fine. You guys are not pure organic chemists yet. You're almost there, though, right? Okay. Okay. So everybody got that? Okay. Now. Okay. So what we've done here, this is a reaction in which we have actually done what we call ring contraction. Note that what we started with, in this case, a 6-member cyclic molecule, and we ended up with a 5-member cyclic molecule. So this is actually, okay, then we go here. This is actually a form of a reaction that we call the Prevorsky reaction. Those of you who are in the session last night, okay? Huh?
It sounds like a Russian.
It was? Yeah.
It sounds like Russian.
In Russian? Yeah. I mean, a lot of Russians did organic chemistry.
I know this.
Okay. Then is that Markovnikov, is that a Russian too?
I took Markovnikov.
Okay. Yeah. Okay. So anyway, Prevorsky reaction. Now, in this particular reaction, anytime you have a cyclic ketone in which you have the alpha carbon, you have a bromine or chlorine or iodine attached to the alpha carbon, say like here, and if you add hydroxide, you are also going to get a ring contraction, in which this time you get a 5-member ring. So that last reaction we gave you was almost a variation of the Prevorsky reaction. Okay? For those of you who are interested in the mechanism of this, you should watch the webcast of the session of last night. Okay? Or you could come and see me after the class. Okay, anyway, so this is anytime you have a cyclic ketone in which you have the alpha carbon is halogenated, and then if you have hydroxide or a base, you get a rearrangement in which you get a ring contraction. We call this a Prevorsky reaction. Okay, now, yes. Oh no, okay, very good question, very good question. Now it has to be generally this it's either an 8-member ring, 7-member ring, 6-member ring, maybe sometimes a 5-member ring ketone. Because the reason for that, it's easy to make a 6-member ring ketone. It's easy to make a 6-member ring or 5-member ring, but 4-member rings are very difficult to make because they are strained. Okay, so generally we'll say anywhere from 8-member ring, 7, and 6. Okay, because this will become a 7-member ring, the 7 will become a 6-member ring, and the 6 will become a 5-member ring. Those generally will rearrange to give you the appropriate ketone. For example, if you have this, that would be a 7-member ring ketone, and if you have this here, right? And then you have hydroxide. So you could get a Pfeffersky reaction. And in this case, what kind of product are you going to get? Cyclohexane carboxylic acid, yes. In this case, you get cyclohexane carboxylic acid. Okay? Now, a complementary reaction that allows you to expand the ring. This is the last new reaction I will give you before the exam. From now, no more new reaction. Okay? A complementary reaction to the Pfeffersky reaction is a ring expansion. There is no name for this. If you have, this case, say you have a 5-member ring, cyclic ketone, and you want to go to a 6-member ring cyclic ketone, this is cyclohexanone. To do that, this is the reagent you need. This we call diazomethane. Diazomethane. Okay? Can anybody give me, can anybody help me out in working out the mechanism for this? Yes, this molecule is called diazomethane. Okay? Okay, if you use this molecule here, react with a cyclic ketone, you could expand the ring, and after you expand the ring, you also lose nitrogen. Okay, any idea? Yes, come in. Okay, the methylene group acts as a nucleophile. Yeah. Okay, attack the carbonyl. Well, keep in mind we have to expand the ring. Okay? Okay, this is going to act as a nucleophile. Is that what you are saying?
I don't know where your ring is.
Oh. You don't know what I'm saying?
Yeah, because I said the electrons about the CH2. Yeah. Okay. Are they attacking the carbon that's attached to the ketone?
Okay, let me do the number again, so you give me the numbers. Okay, this carbon 1, 2, 3, 4, 5. So yeah, this is a classic. It's similar to almost like nucleophilic acyl substitution reaction, if you think about it. And what happens there? You have a nucleophile. The nucleophile will attack the carbon of the carbonyl. So that's the classic reaction of carbonyl compounds. Okay? So in this case, this here will attack, just like all nucleophilic reactions, attack this. And then what happens to the pi electron? It goes to the oxygen. Okay, good. So in a way, this is similar to the last example that we gave you. So now we get this intermediate. Okay, so we get that intermediate. So what happened after that? Keeping in mind that this is where we want to go. Okay, let me label the number of the carbons. This is 1, 2, 3, 4, and 5. So what happens? Carbonyl will reform? Okay, carbonyl will reform, okay. So once we reform the carbonyl, then what bond will break? 1 and 5, exactly. Very good. 1 and 5 will break. So it's almost another intramolecular SN2 reaction, if you think about it, in which the nitrogen will be acting as a leaving group. Okay, so now we have the bond between 1 and 5 will break, and then in so doing attach this carbon here, and that is how you get the ring expansion. Okay, and then this will leave the pair of electrons, and so you form nitrogen. So really it's a very neat reaction. Let me draw it in a way so we can see it. Okay. So we have this here, and then we have this here. Here. So let me label this. The carbonyl is here. Okay, so that would be 1, 2, 3.
You have 7.
I do?
Yes.
Oh, I'm sorry. Thank you. So I'll make that a long. Now I have 6, right? Okay, so that is carbon 1, 2, 3, 4, 5, and 6. So we could then just write it in a much fancier fashion. So that becomes this here. And of course, in so doing, we are also losing nitrogen. So the mechanism is fairly simple. By now, you guys should be able to write any reaction mechanism. You know enough organic chemistry to do that now. So I could throw any structure at you, right? Oh, no, not yet. Okay, anyway, so this is a way of expanding the carbon chain, with a cyclic molecule. So, for example, if you have this, we could decide to go from here. We could go from here. And then we have this here, diazomethane. Okay. Okay, generally this is in ether. Ether is the solvent. And then you get this here, cyclopentanone. Okay, so now once you get your cyclopentanone, you want to make an alpha bromo compound, then how do you do that? Then you can get this here. Now you see where this is going here, right? Now you make your alpha bromo, then you could then do whatever you could do. What kind of reaction, Chebosky? Or you could do what other reaction that do you want to do here? Yeah, you could do Chebosky with this if you want to, but then that will take you back to here. So anyway, so now that is the last new reaction I will give you before the exam. That is the reaction of diazomethane with a cyclic ketone to expand the carbon chain. Okay, so let us go back to our quiz question. Yes.
Like, so you can only add one carbon atom, right?
Yes, yes. Because the diazomethane only has one carbon atom. Yes. Okay, I think we did number 1 already, so okay. So let's go to number 2. Okay, Alona, go ahead and read this first. Okay, thank you. Okay, so now this is actually the last step of the iodoform reaction. This is the last step of the iodoform reaction. Okay, so what are we saying here? We want you to provide the mechanism for this transformation. Okay, you'll be surprised that it is similar to all of the things that we've been doing. So what would be the mechanism? You have hydroxide. You have carbonyl. So it's really becoming very boring, right?
Yeah.
Once you know it, you know it. It's not it's not really that much. Okay, so you have hydroxide, you have carbonyl. Hydroxide acts as a nucleophile. What does it do? Attack the carbonyl carbon. So what else? What's new, right? Okay, so let's do that. So this is another variation of the nucleophilic acid substitution reaction. Okay, so what do you get? Okay, now what happens? Double bond reforms, right? Okay, good. And in so doing, this triiodomethane will leave. Okay, and then you get this. You get that? Okay? And then what happened after that? Okay, this here, they picks up the proton from here, acid-base reaction. Very good. Okay. So now we have this here. And then you have your chloroform. Okay, so now let us name the reaction mechanism. Okay, the first one is from here to here, from here to here. This is nucleophilic acid substitution. Because what have we done? We substituted this for this. No, is that right? Am I saying it right? We replace the triiodomethane with hydroxide. Okay, this is a substitution reaction. So this is a nucleophilic substitution. Nucleophilic acyl substitution. Okay, and then we have the second reaction, the acid-base reaction. Okay, then this here, just a straight acid-base reaction right here. Okay? Yeah, do you have a question?
Yes. If I said SN2 reaction, would it be correct or not?
Oh, no, this is not an SN2 reaction.
Not this second one, but the first one.
This here? This here?
No, the nucleophilic factor substitution.
The nucleophilic substitution? No, it is not an SN2 because SN2 has to involve an sp3 carbon atom. Okay. So let us go to the third one. Oh, by the way, let me give you while we do have time today, so let me give you the mechanism for the iodoform reaction. So by the way, this the online session review session we are going to have tomorrow. We will be using the third exam as for discussion tomorrow. Most of those problems we've done already during the quizzes, but we'll go over them again just in case you have some questions you want to further ask me. Okay, so let us look at the mechanism of the iodoform reaction. For example, let us take this here. Let us use this molecule as an example. We know the iodoform reaction. What do you have? You have hydroxide, step 1, and then step 2. You end up getting a carboxylic acid. So here we are losing a carbon atom. In this case, we are also forming iodoform. Okay, to look for the mechanism of this reaction. Okay, anybody want to give this a try? It's a series of steps. Oh, by the way, I'm sorry. This should be in it's iodine. Iodine is here. Okay, anybody want to give this a try? Yes, Lorenzo. Oh, okay. Okay, we have hydroxide, Natalia. No, okay, not yet, not yet, not yet. Okay, remember the last mechanism we gave you. That was the last step of the iodoform reaction. Okay? So, in other words, we are going to have, yes, are going? Yes.
No, go ahead.
Okay, go ahead.
No, go ahead.
Okay, I thought you were. No, okay, let me give you a hint. We have hydroxide acting as a base. The hydroxide will act as a base. We're going to get acid-base reaction, yes. Ines? Okay, look at this hydrogen here. Look at these hydrogens here, right? Okay, these are fairly acidic hydrogen. The pKa is about 19 or so. Okay, and you have a base. So what we have? You get acid-base reaction? Okay, very good. Okay, so let me go ahead and do this here. Okay, so this hydroxide comes in acting as a base. Pull this proton from here, and you are going to release electron to this carbon. And you form this intermediate. Okay, plus water, of course. And then at this point, this enolate ion now will now attack your iodine. Okay, break the iodine bond. So now you have this. Now, what do you think is going to happen next? We see have hydroxide in solution. I know that hydroxide comes, right? Okay, very good. Okay. So the hydroxide comes. Another acid-base reaction comes to pull this here, releasing a pair of electrons to that carbon. So we form another enolate. Okay. Now, once you form that enolate, that now attacks another molecule of iodine. Now you form this other intermediate. Okay, now what happened after that?
Another acid-base.
Another acid-base reaction, very good. So you can, and this reaction actually, if we have maybe before we leave this semester, I may get them with the organic lab to give us a solution of this. Takes only a few seconds. You just add the two solutions, right away you see the iodoform. So it's not as, the mechanism is longer than the reaction itself. Okay, so anyway, it's one of those reactions that you could use to demonstrate chemistry to high school students. Okay, so you now have the hydroxide comes in again, now pulls one of these protons here. Okay, so now you have that, and then you have another iodine is attacked. And each time here we form iodide. Here we also form iodide. Okay, so now we have okay. You remember this molecule here? Okay, remember this? That's the last one we did, right? Okay, so at this point, what happens? Now you get the nucleophilic acyl substitution, right? The hydroxide comes in now. Comes in, attack this. We've done this already, so we don't need to go too much into this. And then that gives you this here. And then once we reform the carbonyl, and this leaves, that gives us the and that finally gives you the chloroform or the iodoform. Sorry. No. Negatively charged. And then once you add the dilute acid, you then get the free acid. Okay, so that is the mechanism of the iodoform reaction. Okay, what time do we have? Okay, we have 20 minutes to go. One more reaction, then I'll let you guys go. Okay, remember when we, during the session yesterday, I gave you the a molecule of, was it barbital or something? So let's see here. And I told you guys to take a look at it before class today. This molecule here. Okay, this molecule here called amobarbital. Amobarbital. It is this is used as an hypnotic. Used as an hypnotic drug. Okay. Now the interesting part of this is, look at what we have here. You could actually make this here using the malonic ester synthesis, and then also using the nucleophilic acid substitution reaction. Very simple reaction. And you look at this here. This is an ethyl group, right? And this here is isopentyl group. So those are the two alkyl groups that you join to malonic ester. And if you, depending on the type of alkyl group you have here, actually they have well over 1,000 of these molecules used as different types of drugs, and each one of them have different functions. For example, this here, this one here is called barbital. That was really the first of the series of the class of compound called barbiturates. This one is used for insomnia. Okay. Look at the difference. Just an alkyl group difference. This is used as a hypnotic drug. This is used for insomnia. And so we have well over 1,000 of these just by varying the alkyl group attached to this here. Okay. So let us see how we can make this. By the way, this you do not take this on your own, because these are very, very addictive drugs. You don't even want to. You don't want to mess with these guys. Okay. Let's see how we can make this. Let's make the let's make this one here. Okay, how will you make this starting from malonic acid? Okay, what do you do? Let's start with this here, malonic acid. Okay. Okay, you form the Enolate. Okay. Okay, then once you form the Enolate, what do you do? Step 2? Okay, what we want to do here, okay. What we want to do here, this part of the molecule comes from malonate. Okay? And this part comes from urea, which is this here. This is urea. Okay. Okay, so now we want to alkylate the malonate. Okay, very good. You want to use ethyl bromide. Okay, then you want to do 2 alkylation, right? Okay, so 3. Another ethyl bromide, right? Okay. Okay, and that gives us this right here. This, let's use the blue color here. Okay, now what happens here, once you alkylate the malonic ester, you do not complete the malonic ester synthesis. So at this point, you now react the alkylated malonic ester with urea. You see how simple that is. And urea is very cheap. So now I'm not teaching you guys how to make drugs now. Okay, so anyway, so you have this here. At this point, you are going to get your nucleophilic acid substitution reaction. If you look at it, okay, so we are not going to complete this. We have this here, this here. You look at this here, coming here, attacking this, right? Your classic nucleophilic acid substitution, this goes here. Okay, and then when you reform, this leaves. Okay, you want me to just go to the product, right? Save you some time? Okay. Okay, well, I don't want to confuse you. Let's do it the right way. So we get this.
Does it happen at the same time? Does it happen at the same time on both ends?
Yeah, no. One happens first, then the other one goes in, yes. Okay, okay, so you have this. So now you have this. And this one here, you see, I have this on this side. And of course, we have the alkyl here. Okay. So now when this comes back, when you reform this will leave. Okay? And so you get this here. So now begin to have this way. You have your carbonyl has been formed, and this nitrogen is here. And it's attached to carbonyl is here. And then you have this here, attached to here, attached to here. Okay, so the ethoxide that you release right here, ethoxide comes here, picks up the proton from here, and all of these things happen so instantaneously. So, like I said, the mechanism sometimes is longer than the reaction themselves. Okay, so we have this. So now we have this. This here. And then we have this here, which will be attached to, okay, that is this here, and of course this is attached to, okay, and you have this here. Okay, so now you get the picture. So now this series will repeat itself. And once it repeats itself, that's how you then end up getting to here. Okay, the process we went through here, now this will simply just attack this. Okay, this goes here. And that process will repeat itself, and that's how you get to here. Okay, so at this point we have come to the end of chapter 22. So I will see you tomorrow. If you have any questions, take a look at the previous exam before you come in tomorrow. Make a copy of it so we can have a lively discussion. Okay, so we are going to finish all the problems on that particular exam. So I'll see you tomorrow.